I'm Matteo Del Passo, and I'm going to talk about a recent work authored by Michele Favari and me concerning the test generation for feedback bridging faults. It is known that bridging faults are among the most likely defects in the CMOS technology, and this holds for nano-CMOS ICs as well. In this context, we focus on feedback bridging faults that connect a gate output line with a line belonging to its fan-out, thus possibly closing a feedback loop and resulting in a complex behavior that may include oscillations, memory effects, and logic errors. It's worth mentioning that previous works show that some feedback bridging fault can only be detected by exposing the oscillating behavior at the primary outputs of the module under test. Previous works provide accurate fault simulation methods for feedback bridging faults, while known test generation strategies typically provide test vectors that open the feedback loop at the logic level. Works on fault modeling, however, show that this test generation approach may lead to fault escapes since oscillations are not considered. In addition, existing works on feedback bridging faults mainly focus on the circuit part that is directly affected by the fault and do not explicitly consider the problems related to the propagation of oscillating signals to primary outputs and their subsequent sampling by memory elements. We show that the delay variations typical of nanoscale CMOS circuits as well as signal recombinations may mask the propagation of fault effects. This figure shows the main problem targeted in this work with an example of feedback bridging fault that may lead to oscillations when the logic path between lines X and Y is sensitized. When propagating an oscillating signal to a memory element, the output waveform under nominal conditions is only partially representative of the problems related to fault detection. In the presence of delay variations, in fact, we should consider a set of possible faulty waveforms and fault detection becomes a random phenomenon. Therefore, a test for a feedback bridging fault should be characterized by the achieved value of fault detection probability. To analyze this problem, we use the Monte Carlo circuit level fault simulation for a small circuit in the presence of all single feedback bridging faults. In this case, we used test sets that excite the oscillating behavior of each feedback bridging fault and propagate its effects to at least one primary output. The results show that even with small variations of circuit parameters, the achieved fault coverage is rather low, and that the escape probability of faults is relevant. As a consequence, the propagation of fault effects should be explicitly accounted during test generation. When considering the propagation of fault effects, we have also a modeling problem. If a single path is sensitized from the feedback loop to a memory element, the duty cycle of the waveform remains almost unchanged, but the same does not happen if the oscillating signals are propagated along multiple paths that reconverge on a single gate. Here, we have an example of recombination at a NOR gate that results in a duty cycle reduction, and here we have an example of recombination at a NAND gate that conversely results in an increase of the duty cycle depending on the fault-free values of such signals. This phenomena may significantly change the probability to detect the fault and increase the sensitivity of the faulty signal to inertial effects. In order to raise the probability to detect feedback bridging faults, we have exploited a Pseudo-Boolean satisfiability solver and optimizer that allows us to generate test vectors that maximize the number of primary outputs affected by oscillations. As an alternative, featuring a lower computational cost, we propose also a two-step procedure based on a more efficient Boolean SAT solver that attempts to generate tests that produce oscillations on a number of primary outputs larger than a given threshold. Both such techniques require an accurate modeling of the combination of oscillating signals that is achieved by introducing a dedicated algebra. The proposed approach has been validated by using Monte Carlo electrical and logic level fault simulation to account for delay variations in small and large benchmarks, respectively. We first observed that test generation with no constraint on the number of primary outputs to which fault effects propagate provides a very low detection probability. As expected, the Pseudo-Boolean optimization achieves the best results, but in a few cases, test generation requires a high computational cost. This problem is overcome by the Boolean strategy that provides a better trade-off between test quality and cost. Finally, we have also shown the benefits of the proposed algebra when modeling the propagation of fault effects.